here I have two pieces of tape. One piece on the end of this index finger, one piece on the end of this index finger. And I'm going to hold them apart, kind of over this figure here. One at the origin, which I'll hold fixed, and the other which I'll hold here. Now these tape pieces have like charges, so they're repelling each other. The force is therefore in the direction of the force that you see here. If I want to move this piece of tape closer to the other, I have to exert a force. Okay, now it doesn't take much force to exert here. You know, I'm a little tired today, so as I get closer, gosh, it gets harder and harder and harder. I can't really push any harder than that, so I better let it go back here. Okay, so I had to do some work to do that. Boy, you take two pieces of tape on the end of your finger, you can really feel the repulsion. That's really not true, but let's pretend it is. Now, these pieces of tape are small compared to the distance between them, so they approximate point charges. That is, the bits of charge on this tape are not much further, no bit of charge in this tape is much further from this tape than any other bit of charge on this tape. Every bit of charge in this tape is at very nearly the same distance from every bit of charge in this tape as any other. Okay? Now as they get close, that's not necessarily true anymore. Boy, I got stronger there. That was easier than it was before. Okay. Now, pushing the tape together requires some work, doesn't it? Because there's a force of repulsion, and I've got to exert a force through a distance. I get up here, it's getting hard again. Now, if I release it, if I just let go, oh, gee, it just goes right back away from it very naturally. And work is now done on the second piece of tape as it moves away. Now let's try to get a handle on some of the numbers that might be involved in a situation like this, and then we'll try to generalize it symbolically and see what we have. If we have, let's say, a movable 5 microcoulomb charge here and a fixed 3 microcoulomb charge here, they would experience a force of repulsion. If they were separated by a distance of 1 meter, so that this charge is at position 1 meter, 0, the calculation of the force using Coulomb's law tells us that the force is in this direction and has magnitude 0.135 newtons. Therefore, in order to move this charge a little bit closer to the other, I'm going to have to exert a force of 1.35 newtons to overcome the repulsion. Okay? Now, let's say I move it just a little closer, from 1 meter to 0.99 meters. So the point is 0.99 meters 0, right here. Right next to this point, just a little tiny distance. Now, over that tiny distance, the force will increase a little bit, but not a whole lot. So we're going to pretend that it doesn't increase at all. And let's just make a rough estimate, excuse me, and say that to move the charge requires an average force of about 0.135 newtons. It follows then that we're going to do some work, and the work will be force times distance, the force of 0.135 newtons approximately, over a distance of 0.01 meters, gives us work of 0.00135 joules. Okay, so we got to do that much work to move from the 1 meter position to the 0.99 meter position along this axis. Okay, well, how many joules is that per coulomb of this moving charge? Moving charge is the 5 microcoulomb charge. Per coulomb of that 5 microcoulomb charge, how many joules is that? In other words, we could also think of it this way. If we put a 1 coulomb charge here instead of a 5 microcoulomb charge, how much work would it take us to move to the 0.99 meter position? Well, if it required 0.00135 joules to move this 5 microcoulomb charge, then that is saying that we have this many joules per this many coulombs. If we added charge to the 5 microcoulombs here, we would get proportionally more charge. So we have proportionally more work. So the work is clearly proportional to the amount of charge we have here. Again, we can think of that. If we had twice the charge, Coulomb's law would give us twice the force. Twice the force would give us twice the distance. If we had any multiple of this charge, we would get the same multiple of the force, the same multiple of the work, since we're moving through the same distance. So between these 2 points, the 1 meter and the 0.99 meter points, the work per charge is this divided by this, or 270 joules per coulomb. Now you know from the introductory problem set that 270 joules per coulomb is 270 volts. A joule per coulomb is a volt. And the introductory problem set works through these ideas in some detail. The potential difference then between the points is about 270 volts. Let's say that. We say that the potential difference between the 1 meter point and the 0.99 meter point will be about 270 volts. Okay? Potential is the difference in the number of joules per coulomb it takes to move, to bring a charge to a certain position. And we'll see what that means later. But potential difference right now is just the work per unit charge required to move from the first point to the second. This is about 270 volts in this case, or 270 joules per coulomb.